Hello students, myself Professor S.J. Rahman from Department of Civil Engineering, KLS VDIT, Halia. Students, in the last class we have discussed about the effects of flow variation on velocity of flow, as well as we have discussed about the resin velocity. So, the sewage discharge flowing through a sewer does not remain constant all the time, but varies considerably from time to time. Due to this variation in discharge, due to this variation in discharge, the depth of flow varies, and hence the hydraulic mean depth, that is HMD, varies. Due to the change in hydraulic mean depth, the flow velocity gets affected from time to time. Since the velocity developed in a sewer of a given section and grade will be less as and when the flow reduces, it is necessary to check the sewer for maintaining a velocity of about 0.45 meter per second at the time of minimum, that is hourly flow, assumed at about one-third of average daily flow. The designer should also ensure that a velocity of about 0.9 meter per second is developed at least at the time of the maximum flow, and preferably during the average flow periods also. Moreover, care should be taken to see that at the time of maximum flow, the velocity generated does not exceed the scouring value. And related to resin velocity, we have discussed about the maximum and minimum velocities to be generated in sewers. The flow velocities in the sewer should be such that neither suspended materials in sewage get silted up nor the sewage pipe material gets scoured out. The first limitation limits the minimum velocity, and the second limitation limits the maximum velocity. We have discussed about the minimum velocities, in which the silting of sewer can be avoided by generating such high velocities that would not permit the solid to settle down. That is, the velocity should be such as to cause automatic self-cleanishing effect. Such a self-cleanishing velocity, that is the velocity with which will even scour the deposited particles of a given size, must be developed in the sewers at least once a day so as not to allow any deposition in the sewer. The generation of such a minimum self-cleanishing velocity in the sewer at least once in a day is important, because if certain deposition takes place and is not removed, it will obstruct free flow, causing further deposition and finally leading to the complete blocking of the sewer. And also we have studied how to determine the self-cleanishing velocity using Schild's expression, that is given by Vs is equal to 1 divided by n r raised to 1 divided by 6 into under root k into d dash into bracket g minus 1, where Vs is self-cleanishing velocity, R is HMD, that is hydraulic mean depth, G is specific gravity of the sediment, D dash is diameter of particles of silt, and N, it is slope. Usually the value of N for sewers is 0.013. And apart from this, we have discussed about the maximum velocities also here. The smooth interior surface of a sewer pipe gets scoured due to the continuous abrasion caused by the suspended solids present in sewage. This scouring and wear and tear of the pipe interior is much more pronounced at velocities higher than what can be tolerated by the pipe materials. This wear and tear of the sewer pipes will not only reduce their lifespan but will also reduce their carrying capacities. In order to avoid these complications, it is therefore necessary to limit the maximum velocity that will produce in the sewer pipe at any time. And also we have discussed about the non-scouring velocities. It mainly depends on the materials used in the construction of the sewers. For vitrified tiles and glazed bricks, the the limiting velocity should be 4.5 to 5.5 meter per second. And for different materials like stoneware, sewers, it should be 3 to 4 meter per second. And the problem of controlling the high velocities generated in the sewers mainly arises in hilly areas where the available ground slope may be very steep. In such places, it may therefore be required to limit the design gradient and to adjust the balance available head by constructing drop through manholes at suitable places along the length of the sewer. And students, today we'll discuss about another two important topics, that is design of hydraulic elements for circular sewer for full flow and partial flow condition. The sewage discharge flowing through the sewer does not remain constant at all the time. For most of the period, the sewers does not run full. When the sewer does not run full, there is a variation in discharge, depth of flow, HMD, that is hydraulic mean depth, velocity, etc. To study these variations, consider the circular section of sewer as shown below in figure, in which the diameter, it shows the depth of flow when the section flowing full, and let H be the section of the sewer or section of the flow when the flow is partially full. In the figure D, as I told you, diameter of circular sewer, H is depth of flow when sewer is flowing partially full, and theta is nothing but angle subtended at the center when the flow is partially full. When when the section is flowing full, the hydraulic parameters will be as follows. First one is cross sectional area, that is nothing but A is equal to pi d square divided by 4, and wetted perimeter is equal to P, that is given by pi into D. This is nothing but the length of liquid which is in contact with surface here. In case of circular sewer, it is pi D, and if the cross section of the pipe is square, then the periphery, that is 4A, if the side of the square is A, then the perimeter will be 4A, like this. And velocity of flow can be calculated using the relation V is equal to 1 divided by N, M raised to 2 by 3, I raised to half here. And hydraulic mean depth, which is nothing but the shown with a small letter M, and it is nothing but the ratio of area to the perimeter. Therefore, by knowing the cross sectional area, that is pi d square by 4 into d square, pi by 4 d square divided and the perimeter pi d, you can say that the hydraulic mean depth as per the relation here for circular sewer when they are running full, it will be d by 4. So that can be found out just by dividing the cross sectional area, that is pi by 4 d square divided by pi d. Then you will get M, that is hydraulic mean depth, as d by 4. And the discharge can be calculated using the general equation, that is Q is equal to A into V, where A is cross sectional area and V is velocity of flow in meter per second. When the section is flowing partially full, the condition is different here, and the hydraulic parameters will be as follows. As shown in figure, depth of partial flow, that will be H, so that can be calculated with a simple trigonometric relations as d by 2 into 1 minus cos theta by 2. Therefore, the proportional depth will be H divided by d, that is equal to half minus half into bracket 1 minus cos theta by 2 here. Now, the cross-sectional area when flowing partially full is equal to, that is pi by 4 d square into theta divided by 360 here, minus d by 2 cos theta by 2 into bracket d by 2 into sin theta by 2. So, this is simple basic trigonometric relations here, and that implies A is equal to d square divided by 4 into bracket pi theta divided by 360 minus sin theta divided by 2. Therefore, the proportional area, that is nothing but small a divided by capital A, is equal to theta divided by 360 minus sin theta divided by 2 pi here. And here, if you take small p as a partial wetted perimeter, then it is given by pi d theta divided by 360. Therefore, the proportional wetted perimeter, that is nothing but small p divided by capital P. Therefore, the hydraulic mean works out to be, which is nothing but the area divided by the wetted perimeter. So, just you substitute in that particular relation to get the hydraulic mean depth as pi d theta divided by 360 into pi d. So, that pi d get cancelled, then you will get the hydraulic mean depth in case of circular sewer when they are running partially full as theta divided by 360. And also we can calculate the proportionate hydraulic mean depth, that is nothing but small r divided by m. Small r represents the hydraulic mean depth when the sewers are running partially full. So that is nothing but, you can say, the proportionate HMD, that is hydraulic mean depth, that is nothing but theta divided by 360 minus sin theta divided by 2 pi, and whole thing divided by theta by 360. So that works out to be 1 minus 360 degree into sin theta divided by 2 pi theta. Now, according to Manning's formula, the velocity of flow small v is equal to 1 divided by n r raised to 2 by 3 I raised to half here, where r is hydraulic mean depth, n is Manning's constant for partial flow, and small n divided by n is called rugosity coefficient here. Therefore, the proportionate velocity is nothing but small v divided by capital V, that is equal to 1 divided by n r raised to 2 by 3 into I raised to half, that is equal to 1 divided by n 1 minus 360 sin theta divided by 2 pi d, as we found out in the previous step, whole raised to 2 by 3 and I raised to half here. Therefore, we can also calculate the proportionate discharge, that is nothing but small q divided by capital Q, as small a into small v divided by capital A into capital V. So that is nothing but proportionate area into proportionate velocity here. So just you substitute all the values calculated in previous steps. So then we'll get proportionate velocity as proportionate discharge, that is small q divided by capital Q, as theta divided by 360 minus sin theta divided by 2 pi into bracket 1 minus 360 degree sin theta divided by 2 pi theta whole raised to 2 by 3. This is when assuming capital N is equal to n here. For different values of theta, all the above parameters can be obtained for different values of theta, all the above parameters can be obtained. Usually, sewer is assumed to run half full or 2/3 full. When the depth of flow decreases below half the full depth, velocity and discharge both reduce. All the above statements are valid only if the rugosity coefficient, that is n small n divided by capital N, does not change with depth here. Let us solve few numericals on design of sewers here. The numerical problem may be asked like this, that is, calculate the velocity of flow in a sewer of diameter 1.20 meter. The sewer is laid at a gradient of 1 in 400. What will be the discharge through this sewer when running one half full? And also they told us to assume n is equal to 0.012, that is Manning's constant in Manning's formula here. Now come to the solution part here. We know that as per Manning's formula, the velocity of flow is given by 1 divided by n into m raised to 2 by 3 I raised to half here. Given, that is n is equal to 0.012 and m is nothing but the hydraulic mean depth, so that can be calculated using the relation A by P, and also in the previous step we have calculated that as D by 4 here, when because this is assumed that the sewer is running half. When the sewer is running half, the hydraulic mean depth works out to be D by 4 here. So diameter is given that as 1.2, just divide that by 4 to get the hydraulic mean depth as 0.30. The slope they have given it as 1 divided by 400. So substituting in Manning's equation, we will get the velocity of flow as 1.867 meter per second. Now use general formula, that is Q is equal to A into V, that is cross sectional area into velocity, to calculate the discharge, and the discharge works out to be 1.056 meter cube per second here. Similarly, the question may be asked like this. Come to the second numerical. Calculate the velocity, discharge and Chase's coefficient for a stoneware sewer running half full. The dia of sewer is 150 mm and it is laid at a gradient of 1 in 60. Assume n is equal to 0.013 in Manning's formula. Now, the diameter given, that the diameter of sewer is 150 mm, that is nothing but 0.15 meter, and n is 0.013 and I is equal to 1 in 60. Sewer is running half full. So as per Manning's formula, velocity is given by 1 divided by n, m raised to 2 by 3, I raised to half here. Now just calculate the hydraulic mean depth using the relation, that is HMD is equal to cross sectional area divided by wetted perimeter. So that we have calculated D as D by 4 when the sewer is running half full. So just you can see the calculation how D by 4 comes here. So that is nothing but the cross sectional area is pi d square divided by 4. Just divide that by wetted perimeter, that is pi d by 2, because here the sewer is running half full. So therefore half of the circumference will be taken as the wetted perimeter. So therefore it works out to be D by 4 here. So by knowing the diameter, that is given as 150 mm or 0.15 meter, just divide that by 4 to get the hydraulic mean depth. Substitute all these values in Manning's equation, that is V is equal to 1 divided by 0.013 into 0.15 divided by 4 whole raised to 2 by 3 into bracket 1 divided by 60 whole raised to half. Now the velocity you can calculate as 1.113 meter per second. Now the discharge can be calculated using the usual formula, that is Q is equal to A into V here. A is cross sectional area and V is velocity of flow here. So just it works out to be 0.01 meter cube per second, or just multiply this with 1000 to get in liters per second. So that works out to be 10 liters per second. Now, according to Chase's formula, the velocity of flow also is given by, that is, V is equal to C into under root mi, where V is velocity of flow, C is Chase's constant, m is hydraulic mean depth, and I is slope. Now, in this equation, you know all the values here. So, you have calculated the velocity of flow as well as you know the hydraulic mean depth, the slope it is given. So, just substitute all the values in this particular equation. That is 1.113, it is the velocity which we have calculated, and is equal to C into under root 0.15 divided by 4 into 1 divided by 60. Then the Chase's constant is works out to be 44.52. Now, the problems in the examination may also be asked like this, that is, design a circular sewer to cater a residential colony in town for the following data. Now, they have given few things here, like first one, area of colony, that is 36 hectares. Second one is population, 10,000. Third one is per capita consumption, that is 180 LPCD, that is liters per capita per day, and critical design rainfall intensity. So that is, they have given it as 4 centimeter per hour. And fifth one is general available slope of ground. It is given as 1 in 1000. And Manning's coefficient, they have given it as 0.015, and runoff coefficient, that is impervious factor, I can say it is given as 0.6 here. To start with the solution, first of all we have to calculate the dry weather flow here. By knowing the rate of water supplied and the population, we can calculate the average DWF, that is nothing but 10,000 into 180. 10,000 is the population and 180 is the rate of water supply. To convert that in liters per second, so just divide the product of population and rate of water supply by 24 by 60 by 60. Then it works out to be 20.83 liters per second. Now, you can assume the maximum dry weather flow as, or I can say it is a factor which is considered in the design of drains here. So just you consider this DWF as 3 times the average dry weather flow here. So just multiply with 3 here. So that is, discharge is works out to be 62.49 liters per second. So just divide this by 1000 to get in meter cube per second or cumex here. Now, apart from DWS, also in the design of sewer, we have to consider the storm water discharge here, which is known as wet weather flow. So, which can be calculated using rational formula which we have discussed in previous class here. So, just to take the discharge due to storm water as Q2, so that can be calculated using the relation, that is AIR divided by 360. So, A is nothing but area to be served by these drains, I is impervious factor, and R is intensity of rainfall. So here A, it is given as 36 hectares. So that is expressed in A is given as 36 hectares only, and A is given as 36 hectares, and I it is given as zero point 0.6, and R it is given as 4. So just to substitute all the given values in this equation, that is Q2 is equal to AR by 360, to get the storm water discharge as 2.4 meter cube per second, or cumex here. Therefore, the total discharge to determine the capacity of sewer will be taken as capital Q, and that is equal to Q1 plus Q2, that is dWF plus WWF. So that works out to be 0.0625 plus 2.4. So then we'll get the discharge, total discharge to be carried by sewer as 2.4625 meter cube per second, or cumex. Now, according to Manning's formula, that is the velocity of flow through the sewers is given by 1 divided by n, m raised to 2 by 3, I raised to half here. Now, n is given as 0.015 and I is given as 1 divided by 1000. Now, you can calculate the hydraulic mean depth, that is m, using the relation area divided by perimeter. So that is nothing but, we will assume the cross-sectional area of flow as full here. Then that means when the sewer is running full, the area will be pi d square by 4, and perimeter, wetted perimeter, will be circumference of circular section, that is pi d. So that works out to be d by 4 here. Now, we know that V is equal to Q divided by A by the general formula. So now just substitute 1 in 1, that will get Q by A is equal to 1 divided by 0.015 into D by 4 whole raised to 2 by 3, that is equal to 1 divided by 1000 whole raised to half here. Now, taking A as pi d square by 8. Now, because at all the time the receivers won't run with with full flow here, assuming sewer runs half full. Now, Q by A is equal to 2.4625 divided by pi d square by 8 here. So here we have to consider the wetted perimeter as the half of circumference, that is pi d square by 8 here. So therefore it works out to be Q by A is equal to 6.274 divided by d square. Now substitute all the values in equation number 2, then we'll get 6.274 divided by d square, that is equal to 1 divided by 0.015 into d by 4 raised to 2 by 3 into 1 divided by 1000 raised to half. Now, squaring on both sides, we'll get 6.274 d square whole square is equal to 1 divided by 0.015 whole square into d by 4 whole raised to 4 by 3 into 1 divided by 1000. Now, just here you can find the value of 1 divided by 0.015 whole square here. Then we will get 6.274 into 0.015 divided by d square bracket square, that is equal to d by 4 raised to 4 by 3 into 1 divided by 1000. That works out to be 0.00886 divided by d raised to 4, that is equal to d by 4 raised to 4 by 3 into 1 divided by 1000. So now d by 4 is equal to 0.00886 divided by d raised to 4 whole raised to 3 by 4 here. then we'll get 5.135 divided by d cube, that is equal to d by 4. Now just which implies d raised to 4 is equal to 20.54. Just to find the fourth root of d here, then it implies d is equal to 2.129 meter, that is equal to 2150 mm. So therefore we can conclude that use a circular sewer of diameter 2150 mm with a slope of 1 in 1000. And you can refer the book Metcalf and Eddy to solve few more numericals on the design of sewers here. Students, these topics are very important in sanitary engineering and in municipal services, and also if you want to work as a consulting engineer here. This is a numerical which can be solved at home here. So this is the conclusion of design of sewers. Thank you one and all.